All right. In this lecture, we're going to continue our discussion on bonding and talk about secondary bonding. So first of all, let's talk about why secondary bonding is important. It's important in a number of fields. Um, the biggest one being polymers. So we're talking plastics. As you can kind of see here, right? All these sort of commodity polymers that are recyclable, water bottles, any sort of container these days is a polymer, and a lot of those properties are governed by secondary bonds. We also have layered structures. Um, Anything like this, I believe this is talc or mica, where you have these sort of layered mineral rocks. The things holding the individual layers together are secondary bonds. Um, Same thing with adhesive. That is secondary bonds. Graphite also is a layered structure, and those bonds between the layers are secondary bonds. And also things like surfactants. Surfactants are basically what make soaps work. Those are governed by secondary bonds as well. So let's get into a little bit about what secondary bonds are. So secondary bonding involves what we call dipoles. And a dipole is basically some molecule where we have charge separation. And let me sort of explain to you what that means. So take this sort of molecule we have here, where we have this sort of positive charged core, and then obviously an electron cloud, which is negatively charged. And so the charge separation happens when the positive or negative are in different places, right? They're not symmetric. So in this case, they're asymmetric because the positive is over here on the left and a majority of the negative charge is over here on the right. And so if we look at this as a sum, then this left side is positively charged and the right side is negatively charged at this moment in time. And so if multiple of these dipoles, sorry about that, if multiple of these dipoles get together, then the negative sides are going to be attracted to the positive sides, right? And so that's going to give us a bond between those, that Coulombic force between those two dissimilar charges. Same thing we saw with ionic bonding. However, the nature of a dipole here is a little bit different. Dipoles occur a lot of times for a very short time. And so we'll talk in the next slides about dipoles a little bit more. But again, it's a charge separation. And so when we're talking about separation, we're talking about spatially, which separate in space. So different areas of the molecule or atom have different charges. So this can happen with liquid hydrogen. When these two molecules get together, that is the bond keeping them together in a liquid. Okay, so there can be different forms of dipoles that exist. And so this diagram here basically shows a very symmetric distribution of charge, the positive core in the middle and then the electron cloud. And so this is uniform in charge. However, atoms, molecules, they're all vibrating, right? At a given temperature, they're vibrating at a certain frequency. And so momentarily, and we're talking very small amounts of time, that positive charge could vibrate and effectively move to one side of the molecule, and then the negative electron cloud becomes centered at the other side. And so vibrational motion can result in what we call fluctuating induced dipoles. So these things happen to normal molecules for very short times just from vibrational motion. And so they happen for very short times. But the idea is if one of them fluctuates due to this vibrational motion, it can actually induce another dipole next to it, because now we have a charge separation. So this is positively charged, this is negatively charged. That means that this section is going to attract a negative section of that molecule, and so it becomes induced. And so this is a weak type of secondary bonds where we have inducing a neighboring dipole from this vibrational motion. So this is fluctuating induced dipoles. All right. But there also are molecules that are inherently dipoles. So they are always they have a permanent distribution in which part is negative, part is positive. And so these are known as polar molecules. So they have a permanent charge distribution, or what we call a dipole moment. So take HF, for example. This is a type of covalent bonding in which we have unequal sharing of electrons. And so the electron, since fluorine is more electronegative, the electron spends more time with fluorine than it does with hydrogen, leaving behind an electron poor rich region. So this is positive, this is negative. And so these permanent or polar molecules can induce dipoles as well. So if another molecule that's symmetric gets next to it, this difference in charge over here could induce a dipole in that previously symmetric molecule. So polar molecules are very strong causes of dipoles. But polar molecules can also bond with other polar molecules. So if we have HF, again, these are more or less positive and negatively charged, and so if it has another one, it's going to be bonded to that. So polar secondary bonds are stronger than those with some type of induced dipole, because they're always have that charge distribution. And a special example of this is actually what we see up here. A special example of this type of polar secondary bonding is actually called hydrogen bonding. And this is what we're going to see in the next slide. So hydrogen bonding is a very specific type where we're dealing with dipoles or polar molecules where we have hydrogen from the name, but also hydrogen bonded to fluorine, oxygen, or nitrogen. So one of those compounds. And the reason it's so strong is because the electronegative species attracts that electron from hydrogen, but since hydrogen is atomic number 1, that means it only has one electron. That is the lone electron, and so that electron basically is over here most of the time. And so this leaves a bare proton where it's not shielded by any electrons. And so that's a very positive charge, and therefore creates a very strong bond with neighboring molecules. So there's basically just a proton over here. Very limited time does the electron of hydrogen spend over here. It spends most of its time here. So that's the strongest type of bonding when we're talking about secondary bonding.